This is the last problem we will do on formulating weak forms. So these are the equations for equations governing the equilibrium of a Timoshenko beam. You don't need to know what a Timoshenko beam is. It's a higher order beam theory. The beam theory that you have learned is Euler-Bernoulli beam theory, and this is a higher order beam theory which makes some corrections over the Euler-Bernoulli beam theory. Now, the thing to note is in these two governing equations, we have two independent functions, that is W and the rotation phi. So rotation of cross sections phi and W are the two functions, and then boundary conditions are specified for W and phi at x equal to 0, and then derivatives of W and phi at x equal to L. So these things are known, and I have to figure out what is the weak form of this set of equations. Now, if you look at the set of equations here, then we can write it in this particular form. We have to write it, remember, in that AU equal to F kind of form, and we can use this. This will be plus, I'm sorry. This is my A, this is the operator matrix. F is Q0, so the right hand side is Q0, and U is the vector of the functions that we want to find out. Both of these are functions of x. So this is the form of my governing differential equations. This hides two equations, and I'll now have to calculate AU, which is dotted with V dV dx. This has to be equal to this in order for the operator to be self-adjoint. Now here V, I have taken V to be an arbitrary function which resides in the same space as W as U does. So V1 and V1 is analogous to W and V2 is analogous to phi x. They reside in the same space and follow the same boundary conditions that W does. So at 0 and L, U and V have the same boundary conditions. Now I have to evaluate this quantity, and to do that, this is what I do. So I calculate first AU, which is a vector. So AU would be minus, remember, U is W phi x. For ease of writing, I will drop the x and I'll just write it as phi. So this is the first equation. This is the first equation, and the second equation is so this is my AU, and now I need to calculate AU comma V. This is what I need to calculate, where V contains two arbitrary functions, V1x and V2x. Okay, so when I take the dot product with this and V, I will get V1 times minus S d square W dx square plus CF W minus S d phi dx. And the second term would give me V2 into S dW ds dx minus d dx. So this would be AU comma V. I have to show that it is symmetric. I have to check whether it is symmetric or not. Now these terms are easy. This term is easy. This term is easy. Why? because you can immediately see that they're symmetric by applying integration by parts, which is another form of the divergence theorem in 1D. So you have V1. Let me just re-emphasize that this S, CF, D, these are taken to be constants, not dependent on X and Y. Otherwise, the problem would be, the calculations would be very, a little bit more cumbersome, though the idea of the whole thing would remain the same. It would still remain self-adjoint. So I'm looking at this first term. So that is V1 minus S d square W dx square dx, which is similar to this term, which is minus d square phi dx square v2 dx. So both these terms can be treated in the same way. I'll show it for one. So this will become 0 to L d dx of, let me apply the chain rule. So this will become minus S dw dx times v1 evaluated at 0 and L, plus integral 0 to L S dw dx into dv1 dx dx. Similarly, this will become minus d phi dx times v2 evaluated at 0 and L, plus 0 to L d phi dx into dv2 dx. So now when you when you want to calculate a v comma u, when you want to calculate this, you would swap w with v1 and phi with v2. So you can immediately see that if I swap w with v1, phi with v2, these two terms, this term and this term, remains the same. So this term is symmetric, this term is symmetric. This term is obviously symmetric because this is integral 0 to L CF W V1 dV. So this would be, if you swap this too, it will obviously remain the same. This term is symmetric because it is 0 to L S phi V2 dV. Swap phi and V2, remains the same. So this term is symmetric, this term is symmetric. Let us look at this and this. Okay, so so we'll concentrate on those two terms only. Let me write the terms down. So I have minus S this is equal to minus S dw dx v1 0 to L plus 0 to L S dw dx dv1 dx. So I have already proved this. Then I had this term 0 to L CF 0 to L CF W V1 dV. This remains as it is. And then I have the term minus 0 to L S d phi dx into v1 dx, which again integration by parts will lead to minus S phi v1 at 0 to L plus 0 to L S phi dv1 dx. So these are all the terms in the first row A, remember we are evaluating this, and this has two rows, row 1 and row 2, which we wrote in the previous slide. Row 1 is, these are the terms in row 1. So now I add them up, add the 0 to L terms. So the 0 to L terms would be, let's take as dv1 dx common. So this and this gives you dw dx plus phi, and then you are left with this, which is CFW V1 dx. This is dx, I'm sorry, dx. So this is what comes off. So we are calculating V1 times row 1 plus V2 times row 2. So V1 times row 1 is this. V1 times row 1 is this. Okay, now we will do V2 times row 2, and let's do it separately. So V2 times row 2 would be 0 to L, V2 times S dw dx minus d square phi dx square plus s phi dx. We have already dealt with this term and this term. So this term, the second term, becomes minus d square phi dx square dx. This will become d phi dx. Sorry, this is v2 here, times v2, add 0 to L plus this is minus plus 0 to L d phi dx into dv2 dx. So this is what this term will become. The third term, 0 to L s into phi dx, remains as it is, and the last term we can also maintain it in the same way, so that we have from here and here, when we add them together, we will have 0 to L v2 s into dw dx plus phi, just like we had in the row 1 term, plus 0 to L d times this guy, d times d phi dx to dv2 dx minus the boundary term. This is the boundary term, d phi dx v2 0 to L. So again, we don't need to worry about the boundary terms at this stage. We just need to see the volume terms, that is the 0 to L terms. And in the 0 to L terms, if you now want to calculate A V times U, so U consists of W and phi, V consists of V1 and V2. So swap W for V1 and phi for V2. So here you will get 0 to L phi s d V1 dx plus V2 dx plus d V2 dx plus d phi dx. So here we see that This term is fine. This into this is same as this into this, and this into this is same as this into this. The problem is with uh, phi s dv1 dx term. This term has a problem. But if we go back to the previous expression, that is the first part, this part of the expression, so then here we can swap again. So we'll get 0 to L S V1 has to be swapped for W, so dw dx times dv1 dx plus phi becomes V2 plus CF V1W dx. So the first term has no problem, S dv1 dx dw dx, you have it here. The last term doesn't have a problem, but this term is S dw dx into V2, okay, uh, which now you can plug in here. So I have, instead of using this V2s, sorry, where is it? V2 phi s dv1 dx. I can use the term from the first equation, first part of the equation, which is s dw dx v2. So I can use s dw ds times v2 here, and if I do that, then uh, I have exactly what I had before. So this and this are the same. Only thing, this is now coming from the first term, and this I can use in the second term. This is coming from the second term. I can use it in the first term, and I can use the phi s dv1 dx here. So I can use here phi s dv1 dx, which is same as dv1 dx phi that I had here. So, but this term comes from the second term. It comes from v2 into rho 2, whereas what comes from here, v1 into rho 1, is this, which I take to the second term, and then I see that the whole thing is self-adjoint. And now once I have proved self-adjoincy, I can set up the variational principle easily. So I can set up pi equal to half a u this is what I set up, and I have it written down somewhere. So the first term would be half 0 to L W this is the second term. So this is AU comma U, minus FU is easily obtained. FU would be 0 to L Q times W dx. So this will be F dot U. So now this is your weak form, but this can be simplified a little further, and the boundary conditions would come out of it. So if you simplify, let's say this term, if you simplify this term, or let's say we simplify this term here, we have 0 to L minus S w into ddx, ddx of dw dx plus phi. So this is what we have, minus sw into, yeah, I think it is right. Yeah. So this is what we have from this term and this term, dx of course. And then if you now apply integration by parts, you will get minus sw into dw dx plus phi at 0 and L plus 0 to L, minus s dw dx into dw dx plus phi dx. Now in the problem, boundary conditions are specified either on w or on this. If it is specified on this, this is given to be f naught at L x equal to L. So at x equal to L, it will be f naught. So this will be at x equal to L, plus at x equal to 0. This is given as 0, so that would be 0, plus this term would remain. Similarly, you can go through, you can apply things to this term, and finally you will get the result that this variational principle is this. This is the variational principle that you will get for this particular problem. Okay, so this is how we go about checking whether variational principles are available for our for the problem that we have at hand. Again, if you see AU comma U is this quantity, and these are squares, and these are constants which are positive, and therefore this is always strictly greater than 0. So this is a strictly positive operator, and we have proved that rigorously. And once we are able to convince ourselves that we have a strictly positive operator, then we can immediately write down the variational principle, the minimization of which will give us the same solution as the original differential equation. So basically we will have to start from here. Our finite elements will start from here, set del pi equal to 0. That's the Euler-Lagrange equation. And then if we can find a function that sets del pi equal to 0, we are done. Okay, so this is how we go about. Okay.